So now that we've talked about inverse functions, we're going to talk about logarithmic functions. This is still section 1.6, and now we're going to talk about what a logarithmic function is. A logarithmic function is where we can undo an exponential. So if I start with an exponential function of, let's say, f of x equals a to the x, then I can actually think about it being finding its inverse. This is one-to-one. You think about an exponential function, it looks like this, or reflection looks like that. It still is one-to-one. So this function is one-to-one. It all works out, so we can find the inverse. So let's go ahead and say that this is y equals a to the x. Again, finding the inverse, there's no way to get x out of the exponent. So what we've done is we went ahead and we're going to go ahead and switch the x and the y. And because there's no way to get that y out of the exponent like we want to, we're going to create a new function. So that's what mathematicians did, is they just said, well, let's just make a new function. And so we're going to define the log base a of x equal to y. And that is allowing us to undo this. So log base a of x equals y means y is the exponent I need to raise a2 to get the number x. And that gives me my logarithmic function. So my function actually would be that f of x equals log base a of x. So that's my function, that's my logarithmic function, and that's the one we're going to be working with from now on. Well, a lot of times. I do want to make a couple comments about this. One comment I want to make about this is that the log base a of a to the x. A to the x, remember, is the exponential. This is its inverse. So I'm going to take a number and raise it, put it in the exponential function, get a number, put it into the log function, I should get back what I started with. This is true for all x in the domain of a to the x. Well, the domain of a to the x is all real numbers. So for x being all real numbers. The same thing is a to the log base a of x. Again, we're going to put the x into the log function, then get a value. We're going to put that value into the exponential function. That will get me back x. This is for all x in the domain of the log function. So let's talk about what the domain of the log function is. The domain of the log function is greater than 0. And remember, when we found inverses, we switched the x and the y, so the domain and ranges switch. So the domain of a exponential function is all real numbers. The range of an exponential function is x is greater than, y is greater than 0. So the domain of a log function is x greater than 0, and its range would be all real numbers. Now let's talk about some of the laws of logs. There's a couple that we want to work with that we actually like to spend a little bit of time with, that we use in calculus. Log base a of x times y. Well, when you multiply a to the x times a to the y, you add the base, the exponents. So that's the same thing here. This would be log base a of x plus log base a of y. We also can have, the second one is log base a of x over y. Again, when you take an exponential function and you divide, you subtract the exponents. So that's what we're going to do here. We're going to take the log base a of x minus log base a of y. Because remember, the logs are exponents. And then the third one that I want to just mention is the log base a of x to a power, let's call it r. What we can do is we can bring that power out in front, and it's log base a of x. So again, you're raising a power to a power. Remember, we multiply those powers. So that's basically what's happening. We're taking this power and multiplying by this other power. We have such thing as called a natural log. The natural log is anything that is log base E. In the United States, we write this as ln of x for logarithmic natural. Believe it or not, in Europe, they just use log for the natural log and not ln. But in this country, we use this. So if we're using base E, this is what we write. All right, so just a couple of examples. Another example to work with here. I want to find the log base 8 of 2. In other words, I'm asking myself, what power do I need to raise 8 to get the number 2? And the answer is 1/3, because 8 to the 1/3 power is the number 2, because that's the cube root of 8. And the cube root of 8 is 2. Let's do this one, e to the 3 to the natural log of 2. This one we need to do a little bit more work with. I don't like that 3 where it is. I'd rather that 3 was up above. So we'll make this, we use that rule of exponents that lets me bring that 3 up front, the rule of logs. Now the natural log is log base e. So we have e to the log base e, which means we're just going to get whatever number's here. And that's 2 cubed, which is, of course, 8. All right. A couple more things. Another example, sorry, backwards. Another example I want to just work with is a word problem. Strontium-90 is actually a byproduct of nuclear explosions. It has a half-life of 28.9 years. And what I'd like to do is I'd like to find the equation, and then I want to find out how long before 20% is left. So let's go ahead and find the equation first. So the main thing to remember is that we are working with f of x equals some number. We're going to go ahead and use a slightly different formula. I don't like the f of x here. We'll call it p of x. And it's going to be some number which is your initial value, so p0, e to the k times t. This is the basic formula of every exponential function. So we're going to go with this. Now we have shifts and so forth you can do, but this is a basic exponential function. And if I have a half-life, it means half of what I started with is left. So half of what I started with, if I started with p0, is left in 28.9 years. So t is 28.9. Then what I can do is solve for my k. That's the only thing I don't know, because really the p0s cancel out. So the p0s cancel out. So we get 1/2 is equal to e to the k times 28.9. And from there, I can see, oh, I want to get that k out of the exponent, so I'm going to go into logarithmic form. Logarithmic form would be the natural log, because we're base e, k times 28.9. So k is the natural log of 1/2 over 28.9. So that's what your k is, and that's what we can work with. You can then take out a calculator and find out what it is and get an approximation, or you can just leave it just as it is, and then we have that value. So now I can come up with the equation. The equation is my p of x is p0 e to this number, natural log of 0.5 over 28.9 t. And then I can find out what all that is. And then part B, we'd like to know when 20% is left. So if 20% is left, that means 80% is gone. So 20% is what we started with is left. So 20% of what we started with And then we can do the same thing. The P zeros cancel. So we can cancel those P zeros. And it's actually the exact same problem we just finished doing basically at this point. 0.2, sorry. 0.2 is equal to e to the natural log of 0.5 over 28.9 t. Take the natural log of both sides. Natural log of 0.2 is the natural log of 0.5 over 28.9 t. And then solve for t. So t is the natural log of 0.2 over the natural log of 0.5 over 28.9. Last thing I just want to mention is sometimes we need to change bases. We don't like the base we're in. Our calculators only have base e and base 10 on them, so sometimes we need to change bases. The change of base formula is the log base a of x is the log of x. I'm sorry, we're gonna make it the bases we like. So we either have natural log or log base 10. I just did log base 10. I don't like log base 10. We use log base e all the time in calculus. So we're gonna use natural log of x over the natural log of a. And this is known as the change of base formula. It's also, by the way, and I shouldn't have erased this, but it is also log x over log a. And that's how you work with the change of base formula.